I can see a few more people are joining in. Shall okay, let me I think we're good to start now. Good morning, good afternoon, and good evening to all of you, depending on where you're joining us from. Before I introduce the speakers, I would like to extend my thanks to all of you for registering and showing up. Your participation means everything to us. Moving on, I would like to start by introducing our esteemed guest speaker, Dr. Raghunathan. Dr. Raghunathan is a chemical engineer with over 15 years of experience in the chemical industry, followed by 17 years at General Motors R&D in the battery cell area. He retired as a GM Technical Fellow in 2022 and returned to India. In India, he is a professor of practice at IIT Madras, battery advisory committee member for the Department of Science and Technology for the Government of India, as well as a technical advisor for several companies, including Urja. And our primary speaker for today is our very own CTO and co-founder, Dr. Prashant Srivastava. Dr. Prashant completed his PhD from IISc Bangalore before diving headfirst into the world of mathematical models and simulations. He brings with him over 15 years of experience in the CAE industry. Prashant co-founded Urja with a vision of simplifying complex engineering problems in 2022. And now I will hand it over to him to take it forward.
Thanks, Aditya. Thanks for the introduction. So today we are going to talk a bit about cell modeling and why this. What helps it brings when. How we can minimize the uncertainties when it comes to cell predictions, whether it is in terms of its performance or it is in terms of its life cycle. And modeling it, one way of removing these uncertainties is conducting a lot of tests. But if you want to minimize these tests, cell modeling can help you reducing the number of iterations. Before we get into the cell modeling, let me first start by introducing Pooja. We are a 3-year old startup, deep tech startup, you know, with a vision to simplify the complex solution of complex engineering problems. And the way we do it is by combining the physics simulations together with the machine learning models. If you look at the traditional simulation methods, the physics simulations were basically we're trying to address the problem where one would model and try to validate these models, making sure that designs are optimum so that while doing the prototypes, they are minimal. But now that we have a lot of data available as well as a lot of advanced machine learning models available, one can combine all of these things together and make use of the insights from the field in the early design stages to make sure that the designs are robust. And we started by solving it for the batteries because batteries are one complex engineering problems where interplay of a lot of physical phenomena happen, and be it the thermal characteristics of the cells or the structural design of the cells or the electrochemical models of the cells, all of these combined together dictate the behavior of the cells, and that is where these models become very complex. And we at OJA solve all these battery problems at various stages, be it the warranty stage estimations or reducing the accelerated life testing for the cells to gain a better understanding, as well as initial performance calibrations for these cells and cell selections. For all of these things, what is important is that we have a good cell model, and for good cell model, we need accurate parameters to represent the cell behavior, and that is also something that we have expertise at. And today we are going to focus on the parameter estimation problem. And here I would like to invite Raghu for giving the context of electrochemical modeling and take us through the challenges involved.
Thank you, Prashant. Can you hear me all right?
Yes.
Okay. So, in I have a few slides to give this whole approach, the problem context. Um, Again, I work with Urja closely, and to start with, I'll walk through the cell internal process. And if you were to get inside a cell and sit there and watch what goes on when you charge and discharge the cell, that's the internal process. And this cartoon here shows what happens when you discharge the cell. And discharging the cell is delithiation of the anode. And the schematic here on the left side is a cathode electrode, which is coated on a copper, an aluminum current collector typically. And cathode, the orange circles on the cathode are the cathode active material, and the other components of the cathode are the binder and typically the conductive filler. That's on the left side of this. And to the right is the anode, very similar to the cathode. The blue circles on the anode represent the anode active material, and then the binder and the filler. And in between the anode and the cathode is the separator. And so this is a very typical schematic of a unit cell that one chooses for modeling. And again, we are looking at discharge. So what happens during discharge is the lithium from the anode side moves to the cathode side. And that's the Li plus you see in the separator, denoted by the white circles. So let's walk through what happens when we discharge. So starting from the right, the number one is lithium diffuses to the anode particle surface. So the lithium is sitting right through the anode particle, and once the discharge process starts, the lithium from the interior of the anode particle starts migrating to the surface. And this process is called diffusion through the solid or solid state diffusion. And once it reaches the surface of the anode particle, it sees the electrolyte, and that's number two. And when it sees the electrolyte, the lithium then decomposes to give Li plus, which is a lithium ion, and an electron. So that's the reaction that happens at the surface of the anode particle when the lithium migrates to the periphery. And the third is the Li plus that's now generated at the surface first diffuses through the electrolyte contained on the anode side. So look at it as swimming through the electrolyte. That's a diffusion. And then it enters the separator. And similar to what happens in the anode, it now diffuses through the separator. It sees a different porosity, it sees a different resistance as it goes through the separator. And then it enters the cathode side. And again, on the cathode, it diffuses through the electrolyte. The electrolyte is what is filling the space between the particles until it sees the surface of a cathode particle. And this is number 4 in this schematic. And when it sees the surface of the anode, of the cathode particle, it undergoes a reaction similar to what happened on the anode side, but a reverse. The Li plus then combines with an electron to produce Li. So the electron, where is the electron coming from? Remember the charge transfer reaction on the anode side releases an electron that flows through the external circuit, and that electron is available on the cathode side for the charge transfer reaction. So Li plus combining with the electron gives you Li. Now this lithium now migrates into the cathode particle, just the opposite of what it did with the anode. And as it moves inside, it makes room for the other, the trailing Li ions and the Li to come and migrate into, diffuse into the anode particle. So this is the sequence of events that happens when we discharge a cell. What I'm not showing here is the also the gradient that's set up by the potential or the voltage gradient or the potential gradient, and that also drives a similar process, transport process, as shown here. So when we are describing these processes, the model, this is where the model comes in, where the processes that we describe are now described in terms of mathematical equation. You set up equation for diffusion, you set up equation for reaction, and so on. And Prashant will cover in detail what these equations are. So what is needed to describe this for a model? First thing we need are the material properties. And if you look at the cathode side, one is the specific capacity. This is a property of the cathode active material. And another is the open circuit voltage on the cathode side. And then we need the component densities. And we talked about the active material, the binder, and the conductive filler. We need the specific gravity or the density of all these components. So this is on the cathode side. Similarly, you need the material properties on the anode side. Where do we get these numbers? Knowing what these are, we can look them up, and the composite components here are definitely available from the cell supplier, or if it's a very standard cathode or anode formulation, you can get a pretty good guess at what they are and get the values from the published literature. So that's the material property. The next are the design parameters. You need these for the model. These are inputs. What are the design parameters? And to the left is the anode, is the cathode, the particle size of the cathode. In case of an NMC cathode, it's typically about 10 micron. So that's a material problem. That's a design parameter. And then you have the thickness of the electrodes. The cathode can vary anywhere between 70 to 100 micron. The separator, which is much thinner than the anode or the cathode, 15 micron. And the anode, typically for a graphite anode, is somewhere between 90 to 100 micron. So the thickness of the three components, the cathode, separator, and the anode, are examples of design parameters. We need to know them. And similarly, on the right-hand side, you need the particle size for the anode particle, and the porosity, which is the white space in between the particles on each electrode, needs to be known, because these are known because when a cell manufacturer produces these cells, these are the set value. They target these values and they manufacture the electrodes, and hence the cell with these numbers in mind, with these numbers in target. You also need to know the composition of each electrode. What is the weight percent of the active material and the other components? So these are design parameters, and they should be available from the cell supplier, or if you have access physically to a cell, we can open up the cell and tear it down. There's a cell tear down, and through SCM imaging, an optical procedure, we can physically see the size of these materials. For example, the anode particle size can be very readily determined from the design from the SCM analysis. So these are some of the inputs, and then going to the next slide, which is the focus of the presentation today, is the reaction and transport parameters. We talked about transport and we talked about diffusion. That's a transport process. And the diffusivity of the particle, diffusivity on the anode is an example of a transport parameter. And similarly, we talked about reactions, and the reaction constant is a reaction parameter. So we have a set of transport parameters which consists of diffusion coefficients and a set of reaction parameters, which are the reaction rate constants. These are not easy to estimate. There are reported values in literature, but we simply can't pick them up because they are very sensitive, very dependent on the chemistry and the design and so on. So these are typically determined from experimental data. And these are some of the things that Prashant will highlight in this presentation. So let's go to the next slide. So if it's an electrochemical model, here are some of the key considerations, especially when it comes to using these models for quantitative predictions. So the models we saw, the processes we described are for simple charge and discharge within a cell. The models, the electrochemical models are often extended to describe the cell degradation. You describe similarly various degradation mechanisms. It could be particle cracking, it could be SEI layer. You build equations describing these, and that then eventually becomes the life model that predicts the life of the battery cell. You incorporate energy balance into these equations. Prashant will show the equations in a minute. And that leads to temperature predictions. And the model then can be used for thermal management. It can also be used for pack design, including the cooling strategy. So the accurate beginning of model, life model, forms the basis for many models. And getting this model to be accurate is very critical. And the bullets below that tells us the key requirements for getting an accurate beginning of life model. Cell chemistry information, NMC is not good enough. We need to know what type of NMC it is. NMC 811, for example. Cell design data for that specific cell. We need accurate half cell open circuit voltage. This is very critical. And the third bullet item is estimation of the transport and reaction parameters we saw in the previous slide from the experimental data. Again, as I said before, there are values available in the literature. They are only ballpark numbers. If you really want good quantitative prediction, we need to estimate these for the cell at hand and not just rely on what's published in literature. We need to validate the model with experimental data, and there may be data, everything is set up for one type of cell. If there is a small change in the cell chemistry, we need to do this process all over again. Again, these are required if you want good quantitative predictions. And again, to get good model, we need good experimental data. And I've seen claims where people say that they can predict everything without experimental data. That is probably not a good idea. You do need experimental data to calibrate the model and get an accurate estimate of all the parameters involved. And there are a couple of things I'll mention before I turn it over to Prashant. Some of the key features that I thought was very impressive in the work from Urja are one, their ability to deal with the data. The data has a lot of noise. It's a tedious process to set up the data and the cost function for minimizing the error between the experiment and the model prediction. They have come up with a way to deal with the data very efficiently. And the other thing is the optimization of the parameters to minimize the error between the experiment and the model prediction. And I believe they have a very robust and efficient and fast process for doing so. And with that, I turn it over to Prashant. It's all yours, Prashant.
Thanks, Dr. Raghu, for setting the context. Now, the processes that Dr. Raghu described in a mathematical form can be represented by the set of equations that you see on the screen. Now, there are diffusion processes that we talked about. So those are these diffusion equations. Sorry, those are the diffusion equations here for the electrolyte, and then the diffusions in the electrodes over here, and then you have also the potential which drives the migrations of the ions from one place to another. Similarly, same kind of a thing happens on the anode and cathode undergoing similar kind of processes. And then you have the diffusion and migration happening through the electrolyte, which is sitting in the separator. Now, for all of these processes, one needs to know that what is the diffusivity through each of these particles, cathode or anode. What is the diffusivity in the electrolyte? What are the reaction rates once the lithium ion converts into lithium by combining it with the electrons? Or what is the reaction rate when lithium decomposes into lithium ion and electrons? All of these parameters play an important role in describing the cell dynamics, and hence accurate estimation of these parameters is very important to understand when the cell undergoes the charge and discharge process, what what kind of a response you would expect from the cell. Now, all of these parameters, like Dr. Raghu mentioned, can be categorized into two following categories: cell design parameters and model parameters. For design parameters, like we have seen earlier, Dr. Raghu already mentioned that we need to get it either by teardown analysis or if the cell supplier has already shared this information. For model parameters, they are tricky to obtain, and even with conventional experiments, it is very difficult to get hold of these model parameters directly. And that is where we simplify this process by using the HPPC data to obtain these parameters. Now, whatever processes Dr. Raghu described, and also from all of those equations, the overall model development process involves, first of all, knowing the half cell OCVs of each electrode, and you have full cell OCV which you can get from the cell testing either by doing a slow discharge process, and based on this you first calibrate the stoichiometrics. And then you have these cell design and material parameters that are input to us, and these can be available either from the cell suppliers or one has to do the teardown. And the problem that we are focusing here is the model parameters, and these needs to be known to collectively take all of these input parameters and put it into all those set of equations to get a voltage response. Now, in the beginning, because the model parameters are not known, we will never be able to use these models and get the exact voltage response for the cells that we are going to model for. And that is where calibration of these model parameters becomes important, and for which you would need first the test data. You will start by assuming certain model parameters, you compare your response with the test data, and then start iterating over the model parameters, making sure that it is matching your test data. In this particular case, we have HPPC data as a test data to complete this model. Now, why this becomes important to accurately determine these parameters is also understanding the characteristics of the cells once they go through the charge discharge process, because that is very detrimental to the evaluation of the cell performance. What kind of a power availability we have for these cells, what is the charge and discharge time for the cells once you are discharging it at certain C rates. And there are certain important things that you would immediately observe, that if you have diffusivity which is not being accounted for properly, you would clearly see that the CV time itself becomes much more larger if the diffusivity is lower. And also, what it results into is the amount of recovery that the cell shows once you have fully discharged it and put it to rest. All of these things are tightly governed by what the reaction rates are at the particle surfaces and the corresponding diffusivity of the particles. And if we have not determined them properly, whatever cycling response that we are getting from our models is never close to the response that you would expect the cell to have. And this leads to error for multiple reasons. Evaluating the power performance, or be it the fast charging estimates, or even the degradation models. All of these will play a significant role subsequently. And in a similar way, you have also the power feed that happens over the period of the uses of the cells, and the amount of the voltage drop depends on the lump resistance of the cells and also the over potentials which are dependent on the reaction rates. And if you don't estimate these properties properly, you are off by basically estimating these DCIRs, which are again an important parameter for understanding the cell performance. And that basically sets the context that why these parameters needs to be determined accurately for any subsequent performance or degradation analysis of these cells. And we at OJA have come up with an approach where we make use of the HPPC data to identify these parameters, given that the half cell OCDs as well as the design parameters are known to us. So, like we have seen earlier, input requires for the model are design parameters, open circuit potentials, and the other set of parameters, as we have seen, are the transport and kinetic parameters. Instead of that, now the input here is HPPC data, and making use of this as an output, we are going to estimate those model parameters. Now, HPPC data can be obtained from by conducting the experiments on the cells that are going to be used, or there are sometimes these databases where you have HPPC tests conducted. But we would always recommend to conduct the experiments on a particular cell for which you are interested in modeling it, because whatever databases we have may not be the accurate representation for the cells that you are trying to model. Now, one of the challenges with the for any experimental data is that the data comes with a lot of noise because of either the sensor measurements or something happening during the experiment itself. Now, that requires a cleanup of the data before we can make use of this data for optimizing these parameters. So the process that involves after we have uploaded the HPPC data together with the other parameters is that first we perform the cleanup of the HPPC data, and then for the HPPC data there are certain important sections that one needs to look at to understand the cell response, and that is where we have automated this process and we identify these protocols. And once we have identified the protocol, HPPC protocol, we also identify the pulse regions, because those are the ones which show us the cell characteristics. And then once we have pre-processed all this data, it is now ready for the optimization operations for these parameters to match the voltage response that we see experimentally to what we see from the simulations. Now, here is a typical example of an HPPC experiment. Usually what is done is you start by fully charged cell, and then you start giving the charge and discharge pulses. And during these pulses, you monitor the voltage. And there are certain signatures during these pulses in the voltage which are very important to understand the characteristics of these cells. That I'll come down a bit later, but I wanted to highlight at this stage there are various types of problems that you will see in the experimental data. First thing that you would notice is sometimes these pulses are not very flat pulses, and because of something happening in these experiments, you would see that the pulses have this kind of shape. Also, when you zoom into these pulses, the pulses have always this kind of a noise, because even though the current is constant, but the sensor noise pitches in. And to exactly identify that which was the pulse region and which we need to focus our attention at, we need to first clean up this data and make sure that we have identified these pulse regions appropriately. When I say pulse regions, you have the rest period after which you start a pulse, and then you will see that there is a sudden ohmic drop that happens in the voltage, and then you have a slower decay, which is the relaxation part of it, which is from predominantly driven by the diffusion process, whereas the initial drop that you see over here is a combination of the internal resistance as well as the overpotential, which is dependent on the reaction rate. Now, then later you have a recovery period. In the recovery period, you have basically set the current to zero. Now there is no chemical reaction happening on the surface of the particles, and the lithium at the surface is now getting diffused inside. And because the diffusion surface concentration changes, and that leads to this recovery in the voltage. Now, all of these things depend on the parameters that we are talking about here, the reaction rates, diffusion constants, as well as the lumped resistances. Now, we first of all clean up all these things, like I mentioned earlier. After cleaning up, we identify the protocols. Like HPPC test was conducted in what SOC range, whether it was changed from 1 to 0 or 0 to 1, or both charge and discharge portions were present. What were the C rates for these pulses? What were the C rate for discharge pulses? All of that gets automatically identified. And of course, we have identified all these pulse regions, we have marked them so that this is now ready for running the optimizations. So we at Pooja have simplified this, and within a single click of upload of the data and just saying I'm just processing this data, you would get all of these insights, data cleaning done, and the data is also ready to be consumed during the optimization process. Now, let me get into a little bit of details on the optimization approach that we have at OJA for the parameter optimizations. In this case, we are focusing on five of these parameters: the internal resistance, lung resistance of the cell, two reaction rate constants on the electrode surfaces, and two diffusion constants. Now, that gives a set of five parameters, and as you would know that the more number of parameters you have for the optimization, the process becomes very complex and also challenging. And making sure that we have uniquely identified these parameters is a big challenge. Now, what we do here is that we focus on each pulses. Now, the reason behind focusing on each pulses is that these pulses are actually pulse experiments are performed at a specific SOC. So you start by fully charged cell, you do the pulse experiments, and then you slowly keep discharging the cells by 10%, and then do the pulse experiments again. Now, for each pulse profiles, you will get a different kind of a voltage response depending on the SOC. What we do here is that we focus on the pulses at each SOC. We calculate the voltages from the simulation. We look at the experimental voltage curves. We get the error between the model and the experiments for that particular pulse. This is our overall error. And then we start weighing it because there are different portions of these pulses which are different, important in different senses. Like I mentioned earlier, that lump internal resistance of the cell and the reaction rates are important in deciding the initial voltage drop. And then there is the diffusion constant and reaction rates which decide the slower decay of the voltage. And thus these errors needs to be weighed appropriately so that we give equal weightage to the important aspects of these parameters. And once we have all these errors summed for a particular SOC, we minimize this error by subjecting it to the optimization algorithm. And we repeat this optimization process for the set of pulses at different SOCs. So what happens is that in this process, we obtain the parameters at different SOCs by doing the optimizations on each of these individual pulses. For optimization process, if you have some idea on these parameters, you can start by an initial guess which is closer to what you would expect for these initial guesses to be. In that case, you have a higher chance of hitting the optimal solution. But what often happens is that for a given cell, you have no idea whatsoever of what these parameters could be. And in those cases, it is also extremely difficult to come up with an initial guess, which is close enough to what you would expect the what the parameters might, the order of parameters might be. The OJA offers an advanced optimization algorithm. It is called evolutionary optimization algorithm, where what we allow users to do is you start by an initial guess, which might not be as accurate as possible, but what we allow is that the variance on these inputs. So if you have a higher variance, the optimization algorithm already starts trying different sets of initial guesses to see that which one is closer to the global minima. And also you can choose the number of initial guesses that you want to start with. More number of initial guesses, more number of runs it will undergo, and thus increasing the optimization time. At the same time, if you have a larger variance. So what I'm trying to say is that you have an initial guess over here, and if you give a larger variance, this is the set within which, if you consider this as a n-dimensional hyperspace of these parameters, This is the space within which it will start trying these initial guesses. And depending on the number of guesses that you want to start with, it will have those many random guesses within this zone. And if you reduce this variance, then it is going to try the values very close to the initial guess. And let's say you increase the number of initial guesses over here, then it will have much denser population within that bound. And the way it works is that for each initial guess, it tries to get the error in the voltages and finds the initial guesses for which the voltage is minimal. So it might identify certain locations for which the voltage was minimal. From there, it evolves further again in terms of optimization and keeps repeating this initial variance and initial guess process from there on to get to a global minimum. Now, as an output, because I mentioned earlier that for each pulse we are optimizing these parameters, what happens is that you will get the SOC dependence for these parameters. Here is one example for the internal resistance where you would see that at SOC 0.5 you have the lump resistance which is minimal, and as you go to higher or lower SOCs, the lump resistance increases. And here we are also trying to show that even if you have different kind of diffusivities, because the lump resistance value does not get impacted because of the diffusivity, and you will see that each of these numbers have come to the same place. Now, one of the important things again I want to emphasize is that we need to be also aware about the sensitivity of these parameters on the different part of the voltage curves. So when I talked about this lump resistance and reaction rates, you know that this is the part of the voltage curve which is sensitive to the resistance and reaction, and this is the part of the voltage curve which is sensitive to the diffusivity and reaction rates, and then you have a recovery which is solely dependent on the diffusion process. Now, when we do this, because there are diffusion constants for anode and cathode, each of these might have a different kind of a sensitivity, which I will talk about subsequently down the slides when it comes to uniquely identifying these parameters. But now that we have all this process in place, we now want to use this optimization algorithm to actually estimate the parameters for experimental data. But before we get into that, we wanted to start by creating a synthetic data. When I say synthetic data, it is the data, a simulation response for the HPPC current profile that we wanted to start by. And we treat this synthetic data as, let's say, experimental data for optimization solver. So optimization solver just knows nothing about it. It just sees this as experimental data. And idea behind doing this experiment is that we wanted to make sure that the optimization algorithms work well and they are estimating the parameters closer to the reference parameter that we have started with. Now, in this case, synthetic data was generated for an MC cell, which is 4.61 ampere hour cell. And these were the reference parameters that we started with. And as you would see, like in a typical HPPC profile, you have initially charge pulse, and then you have discharge pulse and charge pulses, and then you remove the SOC, and you repeat these kind of sequences till you go to the lower SOC value. Now, with this, what we did was we started by different initial guesses for the diffusivity, and when I say different initial guesses, here I have changed them by order of magnitude. 4e15 being the reference, 4e minus 15 being the reference value, and for all of these things, if you look at the pulses, when we optimize it, each of these could capture the voltage profile during the pulses accurately. And that establishes that even if you are far off from the initial values, you will be able to capture the voltage profiles through the optimization process. Coming to the non-uniqueness part, while we were doing this exercise, what we also realized was that when we optimize these parameters, the set of parameters that we obtained, depending on the different initial guesses, were not all of them close to the target. And that essentially tells that even though we could capture the voltage profiles on the pulses, there are different sets of parameters that can lead to the same kind of a voltage profile. Now, how do we believe that the parameters that we have estimated are the parameters that represent this current cell accurately? And also a bit of more insights into why we were having huge variations in our estimated parameters with the different initial guesses. What we saw was that the diffusion at the negative electrode and the positive reaction rates, they were very insensitive to the voltage response. So we tried varying these parameters and we could see that the voltage response was not changing. And primarily voltage response depends on the time scales of these processes, and we calculated the time scales for the reaction rates and diffusion constants, and we could clearly see that the time constant for positive electrode reaction rates as well as the time constant for the negative electrode diffusion, they were much lower compared to the counterparts. And that is what establishes that these parameters are going to be much more sensitive in dictating the voltage response compared to the other sets. And that is what is the reason for a significant variance in these parameters. Now, in order to ensure the uniqueness, what we also did was, instead of just optimizing the parameters on one single C-rate HPPC data, we created the HPPC data for 1C pulses as well as 4C pulses. And we did the optimizations on both of these cases by varying the initial guesses. And finally, we will end up with set of parameters that are capturing these voltage profiles. Then what we did was that we started matching that which sets from these two experiments match closely. And we could find that for an initial guess of D plus 40 minus 15 and for 1C discharge and for 4C discharge, D plus or 40 minus 15 initial guess, they both led to the parameter estimates which were close enough. And we also could see that they were also close enough to the target value. Basically, with this, what we established is that if we repeat these experiments at different C rates and do the initial guess variation exercise, we have a possibility of still getting to the unique solutions, even if we know that some of these parameters might be insensitive and cannot probably, so they cannot be unique sets to capture that voltage profile. Now, after doing this exercise, we actually took commercial cell experimental data and we repeated all of these exercises. And here you would see that there are so many charging and discharging pulses for optimization. And with this also, we could show that apart from looking at the overall HPPC profile, which is exactly matching, overlapping over each other, we could also match the responses over these pulses. So this is the zoomed in view of these pulses, and we could match the responses from our simulations by doing the parameter estimations with the actual experimental response. Now, with this, we have established that the optimization algorithm works, and we have a possibility of getting the unique set of parameters despite having the multiple combinations giving the same kind of a voltage response. One more thing which I want to highlight here is that it is very important to get the right OCPs for the electrodes to estimate these parameters accurately. Here we ran some experiments where we were looking at the OCVs from the HPPC data. When I say OCVs from the HPPC data, you have a sufficient rest period over here, and we looked at the voltages here and then use them as a OCV values at that particular SOC, and then in between we did the linear interpolation for the open circuit voltage curve. And when we run the optimization with this linearly interpolated OCV curve and obtain these parameters, we could see huge error in these pulses while identifying these parameters. And when we actually switch to the actual OCP values from the experiments, and then the error was far lesser. And that establishes also the importance of having the right set of OCP curves for the electrodes before we get into the parameter identification. Otherwise, the identified parameters would be far off from what we expect these parameters to be. Now that we have established this process, I wanted to get into some of these applications for this. One obvious application for the estimated parameters would be to look at the cell charge discharge performance or the power performance. But today I wanted to basically highlight the fast charging as an application of identifying these parameters. And I don't want to get into the details of this slide, but what I want to highlight here is that the anode potential, once it hits below voltage zero, that is predominantly when the plating starts. And initially, if you look at the anode open circuit voltage itself, uh, it might not be going below zero during the charging and discharging process, but because of the overpotential drops, you would see that depending on the C rate combinations that you are running, charging or discharging the cells at, charging the cell at, you would hit this zero line. This is called the plating line, and beyond which the plating will start. We at OSHA have an application where you can run these experiments where you can optimize the current profile along the plating line to ensure that the degradation is minimized when you do the fast charging. Now, major challenges with the fast charging is, of course, one is the lithium plating, which eventually leads to the faster degradation of the cell. And the other thing is when you do the fast charging, there is a huge amount of temperature rise that happens, and you would not prefer charging the cells at very high temperatures. And that is when we at OJA track both the temperature profiles during the solutions by solving the heat transfer model together with the lithium plating line charging to ensure that the current profiles that we come up with is optimal both in terms of the temperature as well as the degradation. Right. One of the other applications that is very important to highlight here is, I mean, for the beginning of life parameters to be very accurate is the degradation models, because we saw those beginning of life models and the set of equations over there. They are a precursor to any degradation models when it comes to electrochemical modeling of the degradations. And unless you have those base equations right with the right set of parameters, which is close enough to the cell, which is representing the cell behaviors accurately in the beginning of life, whatever degradation estimates you come up with are going to be erroneous because you have not mapped the cell performance well. Now, we at OSHA have also the optimization algorithms for mapping these degradation rates, be it SEI layer growth, lithium plating, particle crackings, or loss of active material. And one can run the optimization algorithms after making the initial model calibrations for the beginning of life to also estimate the degradation envelope that you see over here for the different conditions. And this can be run in the different for different drive cycles as well. So it is not only for the constant discharge, charge discharge C rates, but one can use the real world drive cycle to also simulate the state of health as you cycle during this process. Uh, Other thing that apart from cell modeling, I just wanted to highlight another capability of OSHA, where one can quickly turn these cell models into simplified pack models and run quick design of experiments to optimize the battery pack performance as well. So without taking much time over here, it is just a quicker way. Instead of just doing the CAD modeling, one can easily set the number of cells in X and Y directions or Z directions, or the electrical configurations, and all of these connections get set very quickly. Here is the complete, today we talked about the cell modeling, of course, where the parameter estimation was the highlight, but OSHA caters to, the applications at different, for the entire cell life cycle, where you start by doing the cell selections to cell designs and then degradation and thermal performance estimates, as well as range analysis, to also qualifying these cells for safety. All of this is part of the OSHA suite. And if you are interested in any of those, you can write to us at info@osha.energy. And these are the problems that we solve in an cell with the suite of applications that we have shown: warranty estimations, reduced accelerated live testing, and then cell safety qualification. And then today we talked about the parameter estimation, of course. So there are different things that we do, and this is all I had for the today. And we would we are now ready to take questions on the presentation.
Thank you, Prashant and Dr. Raghu for the insightful presentation. If any of you have questions, feel free to drop it in the chat. I see some questions here already. Um, Let me just read them out to you. So, one question we have is, we receive alpha, beta, and production quality cells from the supplier at various stages of the production process. How can we quantify the manufacturing variability and its impact on these cell parameters? Is teardown analysis required at each stage?
Okay. Yeah. So let's say that we have different types of cells. Let's say alpha or beta graded cells, and we want to know that how we go about identifying the performance of these cells or characterizing these cells for a particular application. One way of doing is, of course, running these experiments, the performance experiments, charge discharge experiments, or be it HPPC experiment, just to know the power. But let's say that we have characterized these cells by using the method that we described today for all of these parameters, because experiments become very costly. You can run one particular experiment to identify the performance of the cell in a particular condition, but then you will have to repeat multiple such experiments, and then we can do the model estimations on different batches of the cells. And let's say that you have an alpha cell for which we have done the model parameter estimations, and now we are moving to the beta cells. You don't have to repeat this exercise all over again, I would say, because the cells are very close. You have already uh, estimated these parameters which are close enough representing that cell. And now what changes from alpha to beta cell place might be a slight variations. And that's where I think that from the initially calibrated model parameters, one can focus on the voltage response differences and tune all of these parameters to make sure that we are matching the voltage response for the new set of cells, let's say beta cells.
So, and I would also add that if it's the same manufacturing line and if it's a cell to cell variability, um, the first thing that one would look at is the open circuit voltage. That's the simplest measurement to make. That you see a variability from one cell to another, I would first look for the open OCB and see if it's different. And if it's not, then just simple charge discharge experiments would be a place to start, because seemingly these are coming out of the same manufacturing line, but you see variability from one cell to another. And HPPC is the next step, which will give you more insight into this. So start with OCD. Tear down may not be necessary. If, for example, your OCD is matched, then there is no reason to expect that there may be anything else that could be wrong. And there are smaller differences, such as uniformity of the coating and distribution of the components of the cell within an electrode, that might explain some of the differences. Your tear down may not tell you exactly which of these is a problem. So one thing to do is to just sequentially do the simplest experiment first, OCB, and then do the charge discharge and see if it makes a difference. Then, if it still doesn't give you enough insight, maybe move to HPPC. So instead of jumping into the whole battery of tests, one would do this sequentially until we get to the root of the problem. And this is a good question and a difficult problem to solve, because seemingly, all parameters are the same. It's coming out of the same manufacturing line, but you see variability. But there are ways to address this. And again, the model is not going to solve this problem. You would need some experimental data to explain why there is a difference from one cell to another.
Okay, I think we have time for one more question. So the question is how to estimate or measure the half cell OCD.
Sure. For half cell OCVs, basically there are these three electrode experiments that one performs. So what you do is basically you tear down the cell and you take these electrodes. For these electrodes now, you uh, you basically start by using the lithium as a reference electrode and look at the potential, relative potential of these electrodes to determine the electrode half cell OCVs.
Yeah, I would also add that, for those who are working with coin cells, coin cell, typically when you build a coin cell, you use an anode and the cathode and the separate. And if you're measuring a half cell OCD, instead of both anode and the cathode, if you're looking at the half cell OCD for the cathode, instead of the anode, you would just replace it with an aluminum foil. But the reason is the aluminum foil has always zero potential. So you would construct a coin cell with the cathode, the material of your choice, the material that you're interested in, where you want the OCD. The reference would be the lithium electrode, and when you do a slow charge discharge, you would get the half cell OCD. I think we don't have enough time to describe the entire experimental procedure, but my suggestion is look up literature, there is information, and or write an email to us specifically on the question, how do I measure an half cell OCD? And we'll be happy to answer that email. It's a very standard experiment, so there's no deep rocket science involved in this. It's easy to do.
Okay, so if I don't want to hold the both of you any longer, but if you can answer one last question.
Sure. I think it's okay.
We have a host of questions here. Let's just do one and wrap it up. Uh, the question is, what advantages does Uja offer compared to other available tools?
Uh,
Sure. Well, multiple of these. One is, of course, the way we handle the data, because data processing itself is one of the biggest challenges. Once you get these experimental data and making sure that you are making sense out of this data. So the data cleaning, data processing, and then also filtering out the important part from the data to make sure that we are easily able to optimize these parameters by focusing on the right portion of the data. The other advantage that we have is, in terms of the optimization algorithms that we have developed, um, in terms of its speed, because typically you would see that the optimization algorithm that I described today would be able to determine these five sets of parameters somewhere between 45 minutes to 2 hours accurately, and that's something that is advantage that we bring to the table. But otherwise as well, if you look at the entire optimization process, it is very tedious to set these things up in any tool, because now if you are doing these parameter estimations, you would first filter out the important portions of the HPPC experiment. You would define your loss function, you will set up optimization solver, and then start optimizing these with the multiple iterations and initial guesses, because sometimes the initial guesses might not be right, which itself is a very time consuming process. We here have simplified all of these things to a great extent, where you just start by uploading the HPPC data with the design and the material parameters, and optimization algorithm is also all set. All you need to do is choose these parameter ranges and the initial values, and also you can choose the variations in the number of variations on the initial guesses that you want, and you are done with it. I mean, now you start running the optimization, you get the set of parameter values for a particular experimental data.
And
And
I would also add that there is enough intelligence built in the tool. For example, OCV mismatch should not be optimized. That should come from experiments that should be established. And often the mistake people make is they are off with the OCV, and all the optimization algorithm does is to make sure that the OCV is matched. And that defeats the purpose of estimating the transport and reaction parameters. That has nothing to do with the OCV. So there is enough intelligence built in that we just filters out the important aspects of the data that is required for the accurate parameter estimation and separates it from the data that needs to be established for the open circuit voltage, for example. That should be accurate. And then because you're in a model, you're not modeling OCV in any model. Electrochemical models uh, basically model the deviation from the OCD. So make sure that we establish the OCD correctly, and then the parameters should explain the deviation from the OCD. And there is enough intelligence built in that it takes care of this requirement from a data and a model establishment point of view. Any more critical questions?
No, I think that's it for now. That's it for now, Dr. Raghu. Well, thank you so much for attending, and thank you, Dr. Raghu, for being here. Thank you, Dr. Prashant, for that insightful presentation. I would like to wish all of you a very good day. And
And I would say a question. Is there an opportunity for people to contact us after the webinar to their questions for clarification?
yes, so follow-up emails will be sent to everyone. The recordings will be shared as well. And you will have the option of reaching out to us and booking a session with our technical experts through a Calendly link as well in the email. Um, if you would like, you can feel free to reach us at info@pooja.energy as well.
So this is not, if the questions are not answered, there is still an opportunity to come back to us.
Yes, definitely. Definitely.
Okay.
All right. Thank you very much. Have a good day.
thank you, everyone.
Thank you.
The recording has been stopped. Thank you for joining. Goodbye.